What's going on, smart people? I gotta be a little bit quiet today because I don't want to wake up Jens. But today I thought it would be kind of fun to...
Shut it! Shut up!
I thought you were asleep. What are you doing up right now?
I'm eating my pistachios right now. It's like 7 p.m. in the morning, Andrew.
7 p.m. in the morning. Yeah, I thought that was video making time. I thought it would be kind of a bonding experience if you and I did a video together. I know you do that charity thing for the tax write-off where you go to homeless people and give them math problems to solve. And I thought we could make kind of a game out of it. Are you down?
No, not really.
Cool, he's down. So, what's going on, smart people? We're back at it with another You Laugh, with a change this time. You Laugh, You Physics. I was talking to Jens, you know him by Flammable Maths, some of you know him by worse names than that. And we got to talking about coming up with a new version of what we did last year, You Laugh, You Differentiate, or You Laugh, You Integrate. Today, it is You Laugh, You Physics, and you should go check out part 1 over on Jens's channel, You Laugh, You Math. And basically, the rules are pretty simple. We came up with a bunch of memes to try to make the other person laugh, and if we're successful, then that person has to answer a physics question. Pretty basic stuff. I don't really know what they're going to be, but I imagine it should be stuff that we can answer in a timely manner. Unless you're me, of course. I think the last video, or part 1, was a testament to that. So I'm excited for this. So you wanna get started, Jens?
Yeah, sure. I would love to get started. Andrew already programmed a random number generator.
Yep, so we each are going to be going through about 8 or so memes, depending on how bad I was at counting for the last video. And we're going to randomly select those memes, so I have this little Jupyter notebook. Here are the memes we've already gone through and some questions that we were told to solve for the math problems. We actually don't need them right now because these are going to be a different batch of problems. They're going to be physics. And we've got this random number generator, 1 through 10, where it's just going to randomly select memes for us to look at. And if we laugh at them, you get the idea. We got to solve some problems. Why don't we go ahead? You're the guest today, so why don't we get started with you? I'm going to select a meme for you. Does that sound good? All right, your meme is... You are going for number 9. Meme number 9.
Let us see. De Broglie writing all 10 pages of his PhD thesis. Equal to blank OMP. Break time. But that one was a good one.
All right, well, let's stop stalling. You got to solve a problem now. So your problem is going to be, it's number 8.
We have to read out the questions out loud. This way the video is going to be way funnier. Zach always jokingly tells us that when Jens' dad sits on his face for precious father and son moments, it's like experiencing a car crash. What most people don't know is that Zach is actually telling the truth. Calculate the mass of the mighty nutsack under the assumption that it corresponds to a 120 kilometers per hour fast car of mass 1,712 kilograms crashing into a tree, coming to a complete standstill in 0.43 seconds.
What?
Okay, so what we just need to do probably is to calculate how much force the car is going to have on the car crash, and then we are going to divide everything by 10 to get our system mass, right?
So basically what we have is our difference in velocity is 120 kilometers per hour, or in other words, it's 120 divided by 3.6 meters per second. And our delta t, so the time it takes, is 0.43 seconds. Meaning our acceleration, which is the same as 120 divided by 3.6 times 0.43 meters per second squared. So meaning the force on the car crash side is 1,712 times 120 divided by 3.6 times 0.48 newtons. And this is something, and if we divide this whole thing by 10, we are going to get the corresponding mass out. If we set this equal to a certain gravitational force. Woo! So the balls of my dad have a mass of 11,888 kilograms.
Seem bigger. But let's move on to the next part. So I guess it's going to be a meme for me. So from 1 through 10.
No, 1 through 16.
My meme is 1 through 16.
Yeah, 16 memes.
Okay. Why was I doing 1 through 10 before?
I have no idea. This is probably why you always got number 8.
I get number 6. And that meme is... Oh my god.
You laughed. Yes.
No, I just felt I felt what he was about to go through, and the air escaped from my lungs.
Okay, yeah.
Air being compressed adiabatically.
Good old thermodynamic memes.
Get 1.
Oh, nice. Perfect question for you.
Andrew's mom, currently situated on planet Joe, that's her brother's name, by the way, tripped over her pot of blue Sonic curry and fell out of the window of her 69-kilometer high penthouse. Planet Joe is light as fuck, though, and has only 1/9 of the gravitational attraction of the Earth. Calculate the time it takes her to hit the ground. Okay, Andrew's mom, situated on planet Joe, tripped over a pot, fell. So we know that the height, what are our givens? The height is 69 kilometers, which is equal to 6.9 times 10 to the 3 meters.
Nope.
And we know that the gravity is 1/pi, the gravitational attraction of Earth. So G sub J, for planet Joe, is equal to 1/pi times G. Yeah, it's equal to pi. I guess that's better. So, I mean, the obvious kinematic equation that we have to use, we have, let's say H is equal to 1/2 G times sub J T squared. So if we solve for T, then we get T is equal to the square root of 2H over G sub J. Okay, so the units work, that's good. 50 times 10 to the third. Opens Jupyter Notebook, but uses the calculator on his computer. 225 seconds-ish.
That is pretty close. I got to 209 something, 210. So you're pretty close with those fucking approximations. But the square root?
I approximated my approximations. So.
Yeah.
Well, your number is 4. Which I don't
Number
think you
4.
had.
Physicists and mathematicians leaving academia for finance like, I make my own economy. Yeah, that one isn't funny.
At least I made that one.
That probably explains why it's not funny.
All right, you win some, you lose some. Let's go. I guess it's back to me for a new meme. SO3. Why is it when something happens, it's always U3? Phi theta.
Sorry.
Euler angle gang. Yeah, that one got me. It got me because I was thinking about rotation matrices earlier. So that was
Nice.
Okay. To get the 100-meter sprinting world record, Usain Bolt. This actually seems like a legit question. So
Yeah.
This seems very
so far.
fun. You
Yeah.
ran with an average speed of 10.44 meters per second. John decided to buy a new washing machine with a drum radius of that many kilometers. I'm not even reading the question right now. A new washing machine with a drum radius and named it Usain because he loves this guy so much. Now he was wondering, how high must he set the machine's RPM to make it spin at the same constant velocity that Usain Bolt was running? Okay, so we need, what's the relationship between rotational and linear velocity? So we know V should be equal to, what is it? Omega times R. So require that omega equal of Usain Bolt over the washing machine. Yeah, so it's about 10.44 meters per second divided by about 10 meters. So let me just say that this is about 1, the frequency is 1 inverse second.
Inverse second. Who says that?
Okay, so the RPM, so if it's 1 rotation per second, then per minute, that's just going to be about 60.
When you see an engineer running through the physics department, get the red.
That was a
Get
laugh.
the red. Yeah, that was a laugh.
So far, you've almost exclusively laughed at the ones that I didn't make.
Yeah. Number 6. Okay. This is the only normal question, basically. Explain mathematically why, when calculating the time of a small object's free fall on planet Earth, mass is basically negligible. So yeah, why does it not matter if you drop something with 1 kilograms or 1 gram, basically in a free fall on planet Earth? I made several videos on this, but what basically is the case is that we got the gravitational acceleration, like the universal one, which is negative g times the big mass times the small mass divided by the radius squared. And this is equal to mass times acceleration. Acceleration is just r double dot. But if we consider the mass or the force from the small object onto the Earth, basically, so we get multiplied by small m. But one thing is, since we are dealing with a two-body problem, it's basically a two-body problem that we have. We also basically have to solve a differential equation with the reduced mass. So this is something that you also find in Kepler's laws. So if you have the reduced mass, this is the opposing mass that you got. So we are dealing with the force from the small mass onto the Earth, and then the reduced mass is the opposing mass divided by the addition of the two masses. But when we assume that the big mass is way bigger than the small mass, then it's basically going to vanish in the process. Down here, it's like adding 0 to the big mass. This 1 is going to just turn into 1, leaving us with the differential equation negative g times big M times small m divided by r squared is equal to small mass times acceleration, and then we can cancel out the small mass. And this should, I think, be the reason why it's negligible.
I thought it had something to do with like at a certain point, like the parameters that show up in Newton's law of gravitation, the m1 or m2 or little m big M. At a certain point, you identify the mass that shows up there with the inertial mass that shows up in F equals ma. So you're identifying the gravitational mass with the inertial mass, and I thought that's what allowed them to cancel. So what you're saying is when you're writing things in like a center of mass frame, you can treat it as if all of the mass comes from the planet anyways, and not it comes from the bigger object anyways. I see what you're saying.
But I could be wrong. I leave it to the commenters to decide if it was wrong or right.
Okay, here we go. I don't know the difference between B and H in magnetism, and at this point I'm afraid to ask. What's fun?
I asked my theoretical physics professor back in the days, and he just said that H is something like B, just with another factor, but it's basically the same because the factor is so small. I think it was just mu or something. I can't remember for shit.
But yeah, I think the answer to that question depends on whether you're in undergrad or grad school, because undergrad you'll call B the magnetic field.
Yeah.
And in grad school you'll call B the magnetic induction and H the magnetic field. I think I laughed though, so I gotta answer another one. I don't like the ear laughing at
The units!
Flammy's fat grandma participates in a wheelchair race. When the race starts, the voluptuous old lady... You wrote these questions, by the way. I want everyone to know that you wrote these questions. The voluptuous old lady accelerates at a constant rate of 6.9 kilometers per minute squared for 17 hours.
No!
Or is that 17 Planck seconds?
No, hectoseconds.
Don't know what hecto is.
100
Calculate
seconds.
geometrically the distance she accelerated in meters, in factorial meters. Alright. So let's go. I guess I'll start by just putting everything in SI, which I'm probably going to do wrong knowing me, which is 6.9 times 10 to the 3 meters. It's about 2. Yeah, can I just call it 2?
Yeah, let's just call it 2. It's about 2.
I'm gonna have to draw this on like a log scale or something. Hectoseconds, which is equal to 17 times 10 to the 100, you said?
What? No, hecto is just 100.
Oh, I thought you said 10 to the 100.
No! Good.
That's why I said I thought I was gonna have to do this on a log scale. So the acceleration versus time graph. And then for all of this time, so the area under this curve is going to give us the velocity.
Nice, yes. Velocity is nice. Andrew got it.
So if the acceleration is constant, then the change in velocity is linear. So the velocity versus time graph. And we're increasing from rest, probably.
Yes, this is why I included the starting line. He's reading between the lines. He should study physics. He's got it in
Lord
him.
knows I shouldn't study math.
Yeah.
Okay, so we're starting at rest and we're going up to about 3,000 meters per second. And it's linear. Okay, so this is, I guess, at GF. And geometrically, oh, I see what you're saying. Now we can just do the area of a triangle.
Yes,
times
exactly.
height times 3.4 times 10 to the 3. Okay, so you get roughly like 4 times 10 to the 6.
4 million meters?
A little bit over 1 million meters. Good job, Grandma. It went for 3 minutes.
What? Damn technical difficulties. God damn it.
You're getting a meme?
Yes. Someone. This is so easy. Solved in over 2 seconds, by the way. Something G. Flammable Maths. And I took the person in. When you started with the O dot something seconds, I knew exactly what was coming. That was... Asshole. You got me there. Freaking
I love India.
mate. Acting like they are
Farther east.
than us Westerners.
Alright, well that part's definitely not getting in the video. Glad I got you to laugh at something I
Finally,
made. Like I gave
finally.
you all of these macaroni arts and you've just thrown them in the trash and said try again up until now.
Oh no. Oh no. Oh.
Yes. Yes!
Sex Daddy trips over his pot of limited Lady Gaga pink chromatic curry.
Curry in 2 questions? Were you eating curry while writing these?
No. And starts sliding down a 57-degree inclined plane for 4.20 seconds. When hitting the ground, he suddenly collapses into a point mass due to something quantum, I don't know. Using Lagrange formalism, calculate his velocity at a given point in time, assuming his initial velocity was 0.
Dude, that's hilarious. So the last meme, something.
Yeah, something.
The question
Exactly.
you have to answer.
Yes,
Something.
exactly. I actually thought that you got an idea for the something from my question. I don't know. So let's imagine we have an inclined plane. And we have a certain mass up here. And it's rolling down the hill with some certain radius r, which is going to change over time, obviously. R times the cosine of phi, and r times the sine of phi. I hope I'm getting the trigonometry right. So r dot, angle is going to stay constant at all times, is r dot sine of phi, r dot cosine of phi. Meaning t is going to be m over 2 times the scalar product of r dot, meaning it's m over 2 r dot times sine squared plus cosine squared, which is 1. Meaning we get that our Lagrangian is t minus u, so m over 2 times r dot squared. I forgot the squared here. Minus m times g times r times the cosine of phi. And differentiating the Lagrange partially with respect to r dot, which is just mr double dot. Oh yeah, mass is cancelling out. I forgot to cancel it out. Negative 9.81 meters per second squared times the cosine of 57 degrees, which is the same as pi divided by 118 times 57, times t, which is 4.2 seconds. That's a job for Wolfram Alpha, I suppose, and I hope this is correct.
What coordinate system? Did you do the rotated one or the...
You can't really do anything wrong or right here, you just have to make a shift in your angle to get yourself either a cosine or sine wave. I probably have the wrong sign here, so I need to take the absolute value of the whole thing, probably. And then I'm going to get something like 21 meters per second.
Yeah.
Okay,
it's
nice.
Who cares if it's
Yeah.
right? I
Who
think it's
who
the
cares?
process.
No one gives a
Shit, yeah, process is right. That's the most important thing.
I used to, as my strategy for figuring it out, I used to be like, well, if I do it this way, I get negative time, so it must have been the other side.
So exactly my approach, exactly.
Okay, 13. Please don't make me laugh. How Italian people sleep. What's the joke?
Nothing. This is from the meme page, memes which are so deep and dank that they return to normal. This is how Italian people sleep.
I didn't get it so hard to where it wasn't funny at first. And then yeah.
But then you just had to
Go on,
laugh. You are not going to
After
recover
Andrew.
from this one.
Oh no. After Andrew, my fat Dotson, finally started working out again, his fat cells started decaying like crazy, and he lost his body mass at the following rate. By the way, I would get a lot of comments anytime I shaved my beard about like how I was getting chubby, and I was like, oh man, yeah, I do have to start working out.
Man.
Then I started working out a lot, and then people were like, you look dangerously thin.
Yeah.
I'm like, okay, maybe don't care about people's comments on your
You
appearance.
shouldn't care.
After a certain time interval t, his mass is only a third as big as before. Formulate the differential equation that describes his weight loss and solve it for an initial mass of 420.69.
This is like the most subtle insult you can do to someone.
After a certain time, his mass is only a third as big as before. Formulate the differential equation that describes his weight loss. So at time t equal to capital T, my mass at that time is equal to 400, is equal to 1/3 my initial mass. So we have one initial condition, so this has to be a first order differential equation.
Definitely.
We don't have any other. Do I want to assume that this is exponential decay or?
Yes, exponential
linear?
decay, right. So what I meant is that your mass is going to decrease by a third after each and every time interval t. Exactly.
Oh, okay.
Yeah.
Well, hold on. So if I do dm over m, and that's
Exactly.
equal to
Yep.
minus c,
Exactly. Yeah.
then that's going to give me ln of m is equal to minus ct plus d. Mass as a function of time is equal to some exponential, which is just some other constant really. So we have some normalization constant times e to the minus ct.
Exactly. Yeah.
And our initial condition said that at t equal to 0, the mass is 420.69.
Yes, exactly.
M of 0 is equal to 420.69. So I suppose that's just what n is. M of t is equal to 1/3 m 0. I think everyone follows from here. We divide, we take the natural logarithm.
Yes,
we
exactly.
solve for
And then
c,
you are
it gives
going
us
to
the
get
difference
something
constant.
like c being equal to natural log of 3 divided by t. Yeah. Natural log of 3 divided by t. And then you are done.
Okay, next May for me. And after that, one more May for Andrew, and then we are done. And it's going to be this one. Wait, momentums without an apostrophe is conserved? Before initial. Always has been. I read it in the wrong direction. I should have. I'm terribly sorry, Andrew.
No worries. Another one I made this morning.
Yeah, I can see that you made
It's
it.
uncanny, man. I don't know how to make you laugh. 3 words better than I love you. Go. Assume ideal gas.
Yeah.
What saved me here from laughing is I despise people who have those Facebook statuses or whatever that are like, need recommendations for blah, blah, blah. And go, like you can just summon people.
Yeah.
Fugacity is negligible. That would have been way better. I should have made this one. Never mind. Okay, and then we are done. The only question which was still left, but we are not going to solve it, we are leaving this as an exercise to the viewer, is whenever Jens has explosive diarrhea, his feces are able to raise his 69 kilogram heavy ass from the toilet seat by 1 meter in 1 second. What is the average force that is being exerted by his anus?
Oh, what a shame we didn't get to that one. Okay.
Thanks for having me,
I've
Andrew.
learned I've only gotten dumber since last year. Well, that wraps up this You Laugh, You Physics. I don't know. I think this one was a lot more split than the last one.
Yeah,
I think you made me laugh probably a bit more with the part one. I'm not sure.
Definitely.
But these are a lot of fun to do. So stressful though. Every time. I don't care how
takes
simple
so
the question
fucking
is.
long. Takes so fucking long.
So be sure to let us know in the comments section which one of these were we really stupid for and we should have gotten faster. Which ones did you solve in 0.2 seconds? And you're 14, by the way. Thank you guys for watching. Hope you all enjoyed the video. Let me know in the comment section if you did. And Jens, thank you so much for joining me today. This was a blast, brother.
Yeah, thank you very much, Andrew. Thank you very much. Don't you have a sponsor to announce for the end of the video?
This video is sponsored by the rotation matrices. Are you interested in certain representations of SO3? Well, look no further because the generators, there's a finite number of them.
Nice.
Bye.